Hi, I'm Eric Lerner. I'm Chief Scientist at LPP Fusion, and I'm going to be talking in this video series about the crisis in cosmology. Now, if you've been paying attention to the subject at all, you've probably been reading quite a bit lately about the crisis in cosmology. We have Scientific American, Cosmological Crisis, New Scientist, Cosmological Crisis. We have even Wired, Cosmology is in crisis. And Business Insider, they're interested too. Crisis in cosmology. So, is there a crisis in cosmology? Damn straight there is. But the real crisis in cosmology, the one I'm going to be talking about in this series, is a lot bigger and has been going on for a lot longer than the one you've been hearing and reading about. Researchers have been talking about this crisis, literally, for decades. Back in 2005, the crisis was sufficiently severe that a couple of dozen colleagues and myself got together and had a conference in Portugal. And the American Institute of Physics published the proceedings of the first Crisis in Cosmology Conference, 2005. You can find in the literature, even in popular accounts, references to the crisis in cosmology dating back to 1995. Now, it's perfectly true that the awareness of this crisis has increased rapidly, especially over the last year. I did a sort of unscientific study of Google references to the term crisis in cosmology. And sure enough, back in 1995, there were about one reference every year. By the beginning of this century, it had gone up to 5 references per year, 12 references. By the latter part of the present decade, it was about 24 references per year. And then this year, 2019, it shot up to 130 references per year. So what's expanded is the awareness of this crisis. This has become a general awareness both in the field and in the popular media. But what's really behind this crisis? Well, the real crisis in cosmology is that, as I wrote back in 1991 in my book, the real crisis in cosmology is that the Big Bang never happened. The real crisis in cosmology is that the underlying model that most cosmologists are working from is invalid. It's not scientifically validated, despite its popularity. So, the first thing I'm going to be talking about in this series is how do we judge the Big Bang theory? Well, when you want to judge a theory, what you have to do is compare predictions to observations that were made after the predictions happened. Now, why after? Well, that's what makes science useful to us. The ability to predict things that we haven't observed is what science has enabled humanity to develop technology that has allowed us to survive and survive on a larger and larger scale at a higher and higher level. So what I'm going to do is basically grade the Big Bang theory against observations. So this is a list of grading the Big Bang theory, and we're talking, of course, about the scientific theory, not the TV show. When I discuss comparing a theory with observations, we're not talking about expecting a perfect grade. any theory is limited in its applicability, and so is going to give some wrong answers outside its range of applicability. But to be useful, it has to give many more right answers than wrong answers, at least in a certain field of applicability. And the Big Bang theory is supposed to be talking about the entire universe. It doesn't matter for judging the validity of a theory whether or not there's a better theory out there. Science isn't judged on a curve. The theory has to be valid in terms of its predictions. To make an analogy, if this was a century ago and someone was trying to persuade you to get onto their airplane, and the airplane always crashed, but they always had an explanation afterwards, you wouldn't consider it a good argument that everybody else's airplane was crashing. To have a valid theory of the control of aerodynamics, you would be waiting for the Wright brothers to come along, and they had a valid theory, which was proved by they could predict that their airplane would stay up. So that's how we're going to be judging this. In the course of the series, I am going to get into the question of, is there an alternative way of looking at the history of the universe, the evolution of the universe, that is more valid? And we will get into that as well. But first, we have to judge, is the Big Bang theory right? Now, over time, the Big Bang theory has become quite complicated. But I want to begin with the bedrock hypothesis of the Big Bang theory, which is that the universe has gone through a very brief but very important period of extremely high temperature, extremely high density. If that period never existed, then there is no Big Bang. So one thing that we know can be predicted, that if the universe was at high density and high temperature, we know from millions of experiments, from our observations of stars, from our development of technology, that when matter is subjected to high density and very high temperatures, one thing that's certain to happen is fusion reactions. Fusion reactions are when the nuclei of atoms come together at high temperature and form the nuclei of other atoms. So, for example, hydrogen can fuse into intermediate nuclei that eventually can fuse into the different compound helium. So scientists long ago determined that if the Big Bang happened, then it was inevitable that large amounts of helium would be produced and small amounts of two other light elements. One is the light isotope deuterium, which consists of one proton and one neutron. Ordinary hydrogen consists of only one proton. Deuterium would be produced in small amounts, and in very tiny amounts, also lithium would be produced. Lithium consists of 3 protons and 4 neutrons. So these were the 3 light elements that would be produced from the Big Bang. And the amount of these light elements, the abundance we would see, is predicted from the Big Bang theory knowing only one variable, which is essentially the ratio during this period of the number of protons, because it was assumed that the protons were formed first, the hydrogen nuclei, to photons, to the particles of light. In essence, to put it in today's observations, if you know the density of the universe, how much matter there is per unit volume, then you can predict these 3 numbers. Well, this isn't a huge prediction, but it's a prediction of something important. So this is the first key prediction of the Big Bang theory, which is called the Big Bang nucleosynthesis predictions. So back in the 1980s and 90s, people said, well, it was very difficult to actually measure how much matter there is in the universe because it's very irregularly clumped. It's clumped into stars, which are clumped into galaxies. So it's very difficult to get an average. So they said, all right, let's measure the abundance of one of these three elements, and then that will give us, through our calculations, the density of the universe, and then we can use the density to predict the other two. So now we have one measurement gives two predictions. Not a big gain, but it's something. So let's see what happened. Back in the 1990s, people measured the abundance of helium from the spectra of galaxies, the abundance of deuterium, basically from various measurements, including the abundance of deuterium in our own solar system, and the abundance of lithium, again from spectra in very old stars. And from this, they obtained a measure, which they called eta, of the density of the universe. And they said, well, everything's consistent if eta is around between 3 and 4. And you get lithium down here, and that seems to be about right. This is an abundance of 10 to the minus 10th compared with hydrogen. Deuterium's in this wide range here around a few times 10 to the minus 5th. And helium, which is the second most abundant element in the universe, is way up here at about a quarter the mass of the universe. Well, time went by, and observations got better, and we'll get into the story more in a coming episode. Cosmologists decided that they could actually determine the density of the universe. They could predict the density of the universe by measuring the cosmic microwave background. Cosmic microwave background, of course, is a very even glow in the microwave part of the spectrum, similar to the part of the spectrum we use for cell phones, that comes from all directions. But it has very tiny fluctuations, and by tiny I mean a few parts per 100,000, tens of parts per million. And cosmologists thought that by measuring the pattern of these fluctuations, basically the size, they could derive an estimate, a very accurate estimate, of the density of the universe, and therefore they could make much more precise these predictions about the light elements. Again, we'll be getting into the details of how they think they can do this. But let's just look at this part of the prediction. So when we get to basically the present day, after satellites like WMAP and Planck have made very accurate measurements of the cosmic microwave background, now we have this picture. Again, this dimension is the density of the universe, and this is the abundance of lithium, deuterium, and helium. Well, the first thing you notice about this graph is that there's very precise measurement now of the density of the universe, which is around very close to 6 in these 80 units of measurement. It's not at all the same place. 3 to 4, 6. It's not the same number. It's not even close. It's basically wrong by a factor of 2. So the first thing is, if these measurements back in 91 were considered a prediction of what would be found when they took these measurements and these calculations of the cosmic microwave background, we would have to say that's a pretty poor prediction. It's off by a factor of 2. and much larger than the errors. Second thing to notice is these horizontal bands in both diagrams are supposed to be the observations. But if you look at the observations of helium in the present time and the observations back in 1991, well, they don't even overlap. The observations back in 91 was that the abundance of helium was between 22 and 24% by weight, by mass. The observations in this recently published figure, the range is 24.5 to 26.25%. The ranges don't overlap. Well, you can imagine that as measurements got more precise, the ranges would narrow. But why would they move entirely? Well, this gets into a subject we'll be discussing a lot, which is how scientists fool themselves and other people by using incorrect techniques to get the results that they expect. Now, this is an article that was written by Regina Nuzzo and was published in the prominent magazine Nature back in 2015. And the author describes some key, very common methods by which scientists make mistakes and deceive themselves. And one of the four that she mentions is asymmetric attention, rigorously checking unexpected results, but giving expected ones a free pass. Well, that's what happened here. The observations of galaxies that had too low a helium measure for the predictions that were subsequently made subsequently to these observations, researchers found reasons, observational reasons, theoretical reasons, other reasons, to throw those observations out of the sample and to make adjustments to other observations until the answer came out that the observations matched the predictions. And at the time these new predictions were first made, at the beginning of this century, none of the helium observations were as high as the predicted range, the predicted value, which is about 25%. None of them. But now we have complete observational agreement because the observations that didn't fit were thrown out. Now, the situation is really worse than that, because in the course of the first decades of this century, scientists realized with better observations that there were other ways of measuring the abundance of helium. In theory, you can measure the abundance of helium in older stars directly. Now, if you could do that spectroscopically, that would be great. But the problem is helium has to be heated very hot to observe its line in a distant star. So we can only use indirect methods. Now, there's a very good indirect method, which is based on a combination of measuring the luminosity of a star, how bright it is, intrinsically, not how bright it appears to you at the distance you're seeing it, how hot it is, which we can measure from its spectrum, and how much of heavier elements than helium, carbon, nitrogen, oxygen, which in the strange terminology of astronomy are all called metals, how much of these are present in the star, which can be measured spectroscopically. If you put that together, you can combine that with our very good theories of how a star evolves, which is partially based on our abundant observations of our nearby star, the Sun. And you can determine what the level abundance of helium is in the star. And if the Big Bang theory is right, as you go to lower and lower metallicities, less and less carbon, nitrogen, oxygen, and therefore you're looking at stars that are formed closer and closer to the origin of our own galaxy. So they haven't been contaminated with the carbon, nitrogen, and oxygen made by other stars. And you should converge on this 25% level. Well, people did these studies, and lo and behold, they had a crisis. Because what happens is, as you go down in Z, which is the letter they use for this metallicity, as you get to purer and purer, more pristine stars, the abundance of helium first starts going down rather slowly, but then it drops very quickly, and it drops way below 25% to 20%, 15%, 10%, and even below, down to a few percent as you get closer and closer to zero carbon, nitrogen, and oxygen. So what this data said was that the first stars in our galaxy had no helium in them, or at least less than 10%. A complete contradiction to the predictions, the very precise predictions of the Big Bang theory. So this was called the helium problem, and it started back in about 2007 and has only gotten worse. And people have, of course, tried to figure out all sorts of reasons why the theories might be wrong, the observations might be wrong, but they haven't been able to come up with anything. Fact is, the predictions of the Big Bang for helium abundance are simply wrong. So, if we want to start grading the Big Bang theory, we start with the predictions of the light elements. For helium, we have to give the Big Bang 0. Well, can the theory do any better with lithium? Well, actually, no. It does even worse. So lithium, the situation is much more clear-cut, because with lithium, we can measure directly, spectroscopically, because each element produces certain lines in the spectrum, the amount of lithium in older and older stars. And again, what we're talking about older and older is stars that have less and less carbon, nitrogen, oxygen, iron in their spectra, because less and less other stars have lived before that star was created, and therefore less and less of the material of other stars was incorporated into it when it was formed out of the plasma that exists in the galaxy. So if we look at the lithium predictions, this is a graph of lithium in parts per billion relative to hydrogen, and iron in parts per billion. Now, iron is a good marker because iron is only produced in supernova. So you definitely have to have stars living their entire lives producing iron. That's incorporated into the star we're looking at. So if there's less and less iron, fewer and fewer other stars have lived before that star. It's an older star. Well, people have known for decades that if you look at these older stars, the level of lithium in them is about 4 or 5 times less than the amount that was predicted. So again, this isn't even close. But what's worse than that is, again, in the last 20 years, people have found older and older stars. And when you get below about 6 parts per billion of iron, the amount of lithium gets less and less, and in fact, it approaches 0. So, statistically speaking, the amount of lithium in the oldest stars is consistent with zero, with no lithium having been produced before stars started to form in our galaxy. And the upper limit is somewhere around 20 times lower than the predictions of the Big Bang. So if we look at these two elements together historically, what we see is that observations have gotten better and predictions have gotten more precise. The gap has grown and has grown at an accelerating rate. So this is a graph of the number of standard deviations by which the observations don't match the predictions. A standard deviation is just a measure of your expected error. If you're 2 standard deviations off, well, that could be expected by chance 5% of the time. But if the standard deviations keep going up and up and up, until today, the helium observations are about a dozen standard deviations away from predictions. And with lithium, there are about 24 standard deviations. The chance that your predictions are correct is essentially 0. So, with lithium, as with helium, we have to give the Big Bang Theory a grade of 0. Well, what about deuterium? Well, story's different with deuterium. Deuterium can be measured in the spectra of distant galaxies, distant quasars, and by George, it actually comes out pretty close to the predictions. So we have to give the Big Bang Theory a pat on the back, 100% for deuterium. But you have to remember this theory, this part of the theory, which is a very core theory, only predicts 3 numbers. Of these 3 numbers, 2 are completely wrong. So the overall grade for light elements predictions is 33%. In my book, and I think in your book as well, that would be a grade of F. So that's pretty fundamental, because this is one of the basic predictions of the Big Bang Theory, is that from a hot, dense universe, you get these light elements, including the second most abundant element in the universe, which is helium. Well, is there other direct predictions from this basic core assumption that the universe went through a period of high density and high temperature? Well, yeah, there is. And again, it's not good news for the Big Bang Theory. Scientists know that if you have matter at very high temperatures, and this is much higher than those in the center of the sun, then in the presence of particles of matter, photons can create antimatter and matter pairs of particles. Now, antimatter, despite its strange name, is something that we've observed a lot in the laboratory. It's not that unusual. When a photon passes near a nuclei, it can produce pairs of protons and antiprotons, or at much lower energy, pairs of electrons and anti-electrons. In the conditions hypothesized in the Big Bang, what you would have is a sea of protons and antiprotons produced in exactly equal numbers. As this sea of protons and antiprotons expanded and cooled, the protons and antiprotons would be colliding with each other. Now, a strange thing happens when a particle and its antiparticle collide. they're annihilated. Their energy, the energy that's trapped in their mass, is 100% converted into electromagnetic energy, into gamma rays. So they disappear. So if you start with equal amounts of matter and antimatter, most of that matter and antimatter will be completely annihilated. And you'll only get a very few survivors. And you can figure out how few those survivors will be, and therefore what the density of matter should be in the universe at the present time. So that's a prediction of the Big Bang Theory. It's not a widely noted prediction, but people are aware of it. Problem is, it's much further off than what I've been talking about. The prediction is about 100 billion times less than the amount of matter that we observe in the universe. Now, it's true, we don't know exactly the density, but we know roughly what the density is, and this is 100 billion times less. Well, again, scientists have known about this problem for decades. And decades ago, they invented a solution for it, a hypothesis that had to be added to the Big Bang Theory to make it work. And that was that there was some force that slightly changed the symmetry between matter and antimatter. In our big accelerators and in our experiments, we always observe matter and antimatter are produced in exactly equal amounts. But this theory said, well, for some reason, there's going to be a little bit more matter produced. So when the annihilation occurs, there's going to be 100 billion times more matter left over than is predicted by these calculations based on real symmetry. Well, first of all, no such asymmetry of the nature that would be needed for this prediction has ever been found in our accelerator experiments. But for very basic reasons in our understanding of physics, if this asymmetry exists, then there's an inevitable prediction about the protons that we observe today and that are part of every atom in the universe and every atom in ourselves. And that prediction is that the protons must decay. In our observations in the lab, protons are stable particles. They don't have a lifetime. They don't spontaneously decay the way a radioactive material does. But in order for this asymmetry to occur when the Big Bang was happening, it is inevitable that there has to be some small amount of decay in the proton. And therefore, the proton has to have a finite half-life, where by this time, half of the protons would decay into something else. So the initial prediction for the half-life was a really long period, 10 to the 30th years. That's 10 billion times 10 billion times 10 billion, 10 to the 30th years. Well, how could that be tested experimentally? Well, actually, it's not all that difficult. If you put together 10 to the 30th atoms, and each of them are decaying once every 10 to the 30th year, then just by chance, one of them will decay during a year. And experiments have been set up to observe these decays that would look very different than other reactions that were occurring. Now, you have to shield this experiment from cosmic rays and other things, so most of them are put at the bottom of mines. But if you want to be really sure, you just use a lot of material, because 10 to the 24th atoms sounds like a lot, but it's less than a gram of hydrogen. 10 to the 30th is less than a ton of hydrogen. So if you put tons and tons of material together, then you can measure these very long lifetimes. So people have been doing this for decades, looking for the decay of the proton, and gee, they haven't found a single proton decay. So right now, the upper limit of the lower limit on the lifetime of the proton is 10 to the 33rd years, 1,000 times longer than this gigantic lifetime predicted by the Big Bang theory. But in fact, no protons have ever been observed to decay. So the proton is forever. Again, this is a clear-cut prediction of the Big Bang theory, which is clearly predicted now by experiments in the laboratory, very expensive experiments that have been running for decades. If the proton doesn't decay, then we know for certain that matter and antimatter must be produced, as we observe it in the lab, in equal amounts. And any hot, dense period for the universe would have resulted in 100 billion times less matter than we observe in the universe. So, if we grade the Big Bang theory on its prediction of matter density 100 billion times off, we have to again give it a 0. For its prediction of proton decay, at least 1,000 times off, and probably completely off because it never decays, again, a 0. So 2 more F's on our grading sheet of the Big Bang theory. We'll have more exciting grading coming up in future episodes. Thanks for watching.